Chapter 11F looks at binary, permutation, communication, and dominant matrices. Starting with binary matrices, the word binary typically means just ones and zeros, and that's exactly what's happening here. So a binary matrix is a matrix that just contains ones and zeros. So we could have a 2x2 matrix, that's actually the identity matrix. A 1x3 matrix that only has ones and zeros. So any combination that has ones and zeros is a binary matrix. Now, a permutation matrix, it's just a special type of square binary matrix that contains only one in each column and row. So some examples here are these three matrices are all square and they're all binary. And the thing that makes them a permutation matrix is that in every row and in every column, there's only one. So let's say, take this one for example. In this row, we've only got one. It sits in column 2. In this row, we've got a 1 and 2 zeros. Same thing here. Same here, and here. The word permutation means to rearrange, and that is what a permutation matrix does. What it will do, it simply rearranges the order of the elements in a matrix. So let's look at an example of what this permutation matrix is actually doing. We've got this X matrix, which is a column matrix, a 3x1 column matrix with the letters TAR. P is a permutation matrix, and we can see that it is a permutation matrix. It's square, it's binary, it's got ones and zeros, and we've only got one in each row and one in each column. So we want to find out what is the result of pre-multiplying X by P. So if I'm going to pre-multiply X by P, the word pre, remember, means before. So we're multiplying X, or we're multiplying X by P before it. So pre-multiplying X by P. We're finding Px. So what does Px look like? So I'm going to set it up the way that we've done it so far. So P, and then I'm going to put X at the top there. And we'll see what comes out at the bottom. First thing that we can do is check that Px is actually defined. 2 ways we can do that, remember. This top left section needs to be a square. And we can see that it's a square. We've got 3 columns and 3 rows. So this is a square. And the product Px will be the dimensions of this bottom right region. So it's going to be a 3x1 matrix. The other way we could have done this is that P times X, we've got a P is a 3x3 square matrix and X is a 3x1 matrix. The two middle numbers are equal, therefore Px is defined, and Px will equal the two outer numbers, a 3x1 matrix, which is what we got here. So this is a sort of visual representation of what's happening here. So let's actually work this out. We've got 0 pairs up with T. 0 is the first entry in the row, and T is the first entry in the column. So 0 times T is just 0, so nothing. 0 times A is nothing, and then we get 1 times R. So R gets placed in this top one. We have zeros everywhere except the only non-zero entry is in the second column of row 2. So that's going to pair up with A. We can see 0 pairs up with T, 1 pairs up with A, 0 pairs up with R. So A is what remains in this second place. And sort of following that logic, we've got a 1 here which corresponds to the T and zeros. So the T goes there. So the product Px, what it does is this permutation matrix rearranges the letters tar to spell rat. We move on to communication matrices. So they do look similar to networks. We've got this communication of 4 people. We've got Eva only speaks English, Yumi only speaks Japanese, Kim only speaks Korean, but Wong can speak English, Japanese, and Korean. So what this communication network is showing, and this communication matrix, is that Wong can speak directly to Eva, Yumi, or Kim, because Wong speaks all 3 languages. But Eva does not have a link directly to Kim, because Eva can only speak English and Kim can only speak Korean. So we can see how these 3 friends can directly speak to and from with Wong, but they cannot speak to each other directly. So we can form the communication matrix C, where we've got the speakers on our left, or the rows, and receivers in the columns. So Eva can obviously speak with Eva, but it's not really important information because we already knew that. So we don't need to put a 1 there. We're going to put a 0. Eva can directly speak to Wong. Eva can speak to Wong, and Wong receives the message. So we put a 1 there. See, we got sort of arrows going back and forth. So it's like a 2-way communication link. Eva cannot speak to Yumi, so we've got a 0. And Eva cannot speak to Kim, so we have a 0. When Wong is speaking, though, he can communicate with Eva. So the intersection of Wong with Eva, we've got a 1. Again, Wong speaking to Wong, we already know that, so not important information. We're going to leave a 0. Wong can speak to Yumi, and Wong can speak to Kim, so we've got 1s there. And so on. So Yumi can't speak to anyone except for Wong, and Kim can't speak to anyone except for Wong. So we call these communication links 1-step communication links because we're seeing who can speak directly to each other. So it's only a 1-step link. However, we can see that Eva, for example, has a 2-step communication link with Kim. So what I mean by a 2-step communication link is that Eva can speak to Wong, give Wong a message, and then Wong can pass that message on to Kim on Eva's behalf. So in 2 steps, Eva can speak to Kim. In 2 steps, Eva can also speak to Yumi, and so on. To figure out all these 2-step communication links, what we can do is calculate the communication matrix C squared. By calculating C squared, we can see this here. So C squared is our C matrix multiplied by itself. This is something you would probably do in a calculator, and it spits out this matrix. So what do these numbers in the matrix mean? So say this 1 here means that there is 1 2-step communication links between Eva and Kim. So we look at Eva and Kim, there's 1 way for a 2-step communication link to exist. So we've got a 1 here. It should be noted that the elements on the diagonals, which we've shown in the red circles, they are called redundant communication links. Similar to why there's zeros up here, because they refer to the same person communicating with themselves, which is pretty much useless. So what I mean by this is Eva has got a 1 2-step communication link with herself. So what that means is Eva could speak to Wong, and Wong could pass that message on back to Eva. So there's 1 2-step link with Eva back to Eva. Wong, however, has 3 2-step communication links with himself, because he could speak to Eva and she could speak back to him. He could speak to Yumi and they could speak back to him. He could speak to Kim and they could speak back to him. But obviously, because we're not really interested in how people can communicate with themselves, the diagonals are not important. Another piece of important information that this 2-step communication link matrix gives us is if we're ignoring the redundant links, what we can do is add up all the other ones. So we've got 1, 2, 3, 4, 5, 6. So that tells us in this communication matrix, there are 6 two-step communication links in there. It won't be important for this particular network, but if you wanted to find 3-step communication links, you find C to the power of 3. 4-step communication links would be C to the power of 4, and so on. The last bit of information that is important with communication matrices is the total matrix. So if we add up C, which is our 1-step communication matrix, and C squared, which is our 2-step communication matrices, what we can get is the total number of communication links in that network. So if we add the two matrices together, we end up with this matrix. So what this means is, for example, with this one here, so in total, there is only one way Eva can speak to Wong. Let's have a look at an example of this in practice. We've got Freya, Lani, and May send each other messages, and the 1-step communication links are shown in this diagram here. Now, first thing we want to do is construct a communication matrix C. So because we've got 3 people, we know it's going to be a 3x3 matrix. Let's say we've got Lani, Freya, and May. Yeah. So from Lani to Lani, there's no loop here. So there's no link for Lani to send a message to herself. Lani, however, can send a message directly to Freya. So we've got a 1 here. And she can also send a message to May. Freya can, that should be a 1, because there's only one way that Lani can send a 1-step message to May, and it's sending it to her directly. Freya can send a message to Lani, not to herself, and she can send one to May. May can send a message to Lani. She can also send one to Freya, but not to herself. So that is our communication matrix C. Next thing we want to do is calculate C squared. Now C squared will give us it'll show us what all the 2-step communication links are. Now this is something that we should be doing in our calculator. So if we go keyboard math 2, we can create a 2x2 matrix straight away and then just add a row and column and then just fill in the elements. And we're going to assign C. All right, so now what I want to find out is what is C squared? And it's going to give it to me there. So C squared is equal to, we've got 2, 1, 1, 1, 2, 1, 1, 1, 2. And our final question here is, how many different ways can Mai send a message to Freya? So what we want to do here is figure out the total number of communication links between May and Freya. So we're going to want to find this T matrix, which is C plus C squared. I've just done that one by hand here, going C plus C squared, but even quicker, just put it in your calculator. Because you've already defined this matrix as C, it's handy because you can just find out what C plus C squared is straight away. So it's just a matrix filled with 2's. So to answer the question, how many different ways can May send a message to Freya? So we've got May sending a message to Freya. So it's this element here. It is element 3, 2, row 3, column 2. So we look at row 3, column 2 for our T matrix, and we've got a 2. So there are two different ways that May can send a message to Freya. Now the last type of matrix we're looking at for 11F is the dominance matrix. So dominant matrices are similar to communication matrices. They are often very helpful in sports or when you want to decide when an individual or a team is the most dominant. So we've got this network here, and at first it does look fairly convoluted, but we've also got this matrix here to show what's going on. So we've got in a tennis round robin between 5 friends. So a round robin is when each player plays everybody once. We've got Anne defeated Cass and D. If we just focus on this one to start with, Anne defeated Cass and D. So we've got Anne here, and what that says is from Anne to Cass, there's an arrow pointing that way. We can see that arrow points that way because Anne defeated Cass. And for Anne to defeat D, we've got an arrow pointing that way. But that means that Anne lost to Bob. So Bob defeated Anne, and Emma defeated Anne. If you sort of go through there, what that corresponds to in the dominance matrix is that Anne has not beaten herself. So there's a 0 for Anne and Anne. Anne did not beat Bob, so there's a 0 here, but Anne did defeat Cass. So we've got a 1 here. And what that shows us is that Anne has a 1-step dominance over Cass because Anne defeated Cass. Anne also has a 1-step dominance over D because she defeated D, but she does not have a 1-step dominance over Emma. And we can fill out these 0s and 1s just based on either the diagram or the description that we've got here. Another example being Cass defeated only D. So if we go to Cass has only got a 1 in the D column. So Cass has only got a dominance over D. And this dominance column here is just the sum of how many dominances each person has. So Anne won 2 games. She's got 2 dominances. Bob won 3 games. He's got 3 dominances, and so on. So at the moment, there's a bit of a tie between Bob and Emma. We don't know who the most dominant person is. They both are equally dominant at the moment. To figure out who is actually the more dominant player, what we can do is check their 2-step dominance. Just with the communication matrices, we do that by finding D squared. So we've got D squared here, and we've got different dominances added up. Now, what these numbers are referring to, if we take this 3, for example, where with Bob and D, what this 3 represents is that Bob has 3 separate 2-step dominances over D. The reason for this is because Bob defeated Anne, who defeated D. Bob defeated Cass, who defeated D. And Bob defeated Emma, who defeated D. So on the network diagram here, if we have Bob has an arrow pointing to Anne because Bob defeated Anne, and then there's an arrow pointing from Anne to D because Anne defeated D. So we can sort of follow that link. Now that's very similar to the 2-step communication links from the communication matrices. There's also a 2-step dominance between Bob defeating Cass, who defeated D, and then Bob defeated Emma, who defeated D. And then in a similar way, these dominances are calculated by adding up the rows. So Bob has 6 2-step dominances, whereas Emma only has 4 2-step dominances. So whereas in the 1-step dominance, Bob and Emma were equal, but in the 2-step dominance, we can see that Bob is actually more dominant than Emma. Now again, just as in the communication matrices, we can get the total dominance by adding up D and D squared. So when we add these 2 matrices together, and then we find the dominances by summing the rows, what we end up with is that we can actually rank them a lot better as opposed to the one-step dominance. So Bob is clearly the most dominant. He is more dominant than Emma. Also, what we had before is that Cass and Dee had only won one game, although when we check their total dominances, we can see that Cass is actually more dominant than Dee. Let's look at an example where we can apply this. So we've got 4 of the best AFL players from different teams had their statistics compared when they played each other. After they had each played each other once, the dominance matrix D was created. Using D, decide which midfielder was the most dominant. So we've got this dominance matrix here, and what we're assuming, we've just listed them as A, B, C, and D for simplicity. What this would suggest is that when A played against B, A had better statistics than B. So when A played B, A was the more dominant player. When A played D, however, D was more dominant than A. So if we go to when D played A, we do have a 1 here as well. So what we learned from the previous example, that if we want to find out who's more dominant, what we can do is we can add up the rows to find the dominance. So for A, they were more dominant in 2 games. B and C were only dominant in 1 game, and D was dominant in 2 games. So at the moment, with the one-step dominance, we can't actually decide who was the most dominant. So what we're going to do is we're going to find out the 2-step dominance. We don't necessarily need to find out D squared on its own. We can skip straight to finding T. So if we find out the 1 plus the 2-step dominance in our calculators, we're going to get a matrix that gives us what we need. So we're going to need to put D into our calculators. So we can find out what D plus D squared is here after defining our matrix as D. And this is what we get. So let's write this down. We've got 0, 1, 2, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 2, 2, 0. Now let's add up their dominances. So we've got, I might label them as well. So A has a dominance of 4, 1 plus 2 plus 1. B has a dominance of 2. C has a dominance of 3. And D has a dominance of 5. So now by finding their 2-step dominances, we can actually see that we can rank them all actually. So the most dominant player was D, and the least dominant player was B. Whereas in our 1-step dominance, we weren't able to determine that.